This lecture will be going over classifiers. The content for this lecture is pulled mostly from Chapter 4, Classification, in An Introduction to Statistical Learning with Applications in R. If you have not read this chapter yet, pause, go read it, and come back. The primary topics of today's lecture will be logistic regression, and then we'll move into discussing discriminant analysis, particularly linear and quadratic discriminant analysis. Let's start with an overview of logistic regression. In the past few lectures, we've discussed the ordinary least squares regression problem and regression problems writ large. And remember, regression generally refers to the case where your y, your outcome, response variable, dependent variable, whatever you want to call it, is a quantitative variable, which means that the difference between values or units of a variable has a meaningful mapping to something in the outside world. So 2-unit change in y maps to 2-unit change in the real world. Whereas when your y is qualitative, and what we mean by qualitative is more state specific, that's the context in which you use classification. So you're not trying to model graded changes in a variable. You're more modeling state transitions or affiliation transitions. So how does changes in x mediate some state transition in y? Classically, accuracy is a good qualitative measure. You're either accurate or not. But the 1-unit difference between 1 and 0 doesn't necessarily map into a value that has any quantitative meaning. It's more just defining whether or not the response was consistent with expectations or inconsistent with expectations, at least in the context of accuracy. Now, why do we have separate models for the context of classification? Well, let's think about this accuracy example for a minute. Let's say I have a data set and I'm asking people one question on the street, and I'm determining whether or not they are accurate or inaccurate at this question, and I'm just going to regress that against age. So y is just they answer the question correctly, yes or no. If I tried to model accuracy using a linear regression tool, I would assume that the residual errors are normally distributed. And what I would get is essentially a straight line that's trying to squish residuals where y is binary into a routine that assumes that they're normally distributed. You'll get something out of it. You'll get a straight line. But that line doesn't really capture the nuanced variance between y being 0 and y being 1. If you look at the scatter plot on the left, it's pretty clear to see that as age progresses, people are more likely to go from answering it incorrectly to answering it correctly. There is an overall pattern there. But there seems to be this state, this age, which on average, although not always, transitions people from being inaccurate to accurate. In order to answer this question in a regression model framework, you have to adopt a logistic approach. So logistic regression is a modification of linear regression. And both of them are actually two variants of models known as GLMs, or generalized linear models, where you just have a different formulation of the distribution that y comes from. And if you know what the distribution that y comes from, there's a very general proof that allows for you to build a model, a parametric model, for fitting regression coefficients to that y output. And this only works where y is distributed according to an exponential family. So whenever the distribution for y comes from an exponential, you can find these GLM proofs. And logistic regression is one case where you assume that y is binomial. It's either 0 or 1. And this assumption leads to the assumption that your residual errors are binomial. So if you're trying to fit your regression coefficient, in this case, you're trying to fit the accuracy against age, what you're actually doing is fitting against residuals where the predictions are either correct or incorrect. So you'll build a prediction for y as being either 0 or 1. And your model error is defined as being either correct or incorrect. You either accurately predicted that y was 1 or you didn't. You either accurately predicted that y is 0 or you didn't. So once you have that assumption of binomial errors, or at least residual errors, then you can come up with a solution to the regression coefficients that describe how changes in x contribute to this change in state of y. And with logistic regression, really what you're saying is that this relationship follows the standard logistic function. Now, what I'm showing here at the top is one form of the standard logistic function. So the probability that y is in a state 1, given some particular observation of x, is really just an exponential to some power a over 1 plus that exponential to a power a. And if we just basically insert x's here to, increase or decrease x, what we see is that with a being small, the slope of this curve that you get, this S-shaped curve, is relatively shallow. And as I increase units of a, as I go from 2 to 10 to 100, that transition curve gets steeper. To the point where if you have a high enough value of a, this parameter a, then the transition of y is very discrete. At some point, as you keep turning that knob of x, y goes from absolutely being 0 to absolutely being 1. With lower values of a, which is known as a growth rate parameter, it takes longer to transition. You're more variable in your transition. If you think about this as a probability distribution, so y now just reflects the probability of y being in a state. As I go from left to right on the x-axis, I'm just slowly increasing the probability of y being 1, but it doesn't quickly shift. It's imprecise. So the variance here is related to this growth rate parameter. So lower growth rate parameters means slower transition between states of y. In a regression context, better separation of y as x changes leads to larger a. So all we're doing with logistic regression is replacing this ax term in the model with a regression term, a series of regression coefficients against x plus the constant. That's really what we're just doing here, is we're trying to now fit a logistic curve as opposed to a straight line. Now this state transition function defines how quickly the system shifts between 0 and 1. Another way to frame the problem is by referring to it as the odds of y being 1. So for any given observation and growth rate parameter, what are the odds of observing y equal 1? So the odds are just the probability of y being 1 over 1 plus the probability of y equals 1, which converges to the parameter e to the a power times x. Now, odds are a little tricky here as ratios of probabilities, and that exponential term in particular gets tricky. So often we work with log odds. And by working with log odds, all we're really doing is taking that exponential and getting rid of it. So if we work with the log odds, we now just have a linear summation problem, which is much easier to work with. So like linear regression, logistic regression relies on a set of assumptions to work. And this is largely to do with logistic regression being part of that class of models known as the GLM. So the assumptions of logistic regression are that f of x describes a linear relationship between x and y, same as we showed before. Y is a binary or dichotomous variable, so y can only have two states. There is no collinearity between features in x. And f of x is stationary, just like in the ordinary least squares. So really, you're just changing the assumption about how y is distributed relative to linear regression. And importantly, logistic regression can only work in the case where you have two states of y. It can't work for states greater than 2. Another key difference between linear regression and logistic regression is in how you interpret the models. So for example, let's say that I have a linear regression problem that boils down to any prediction of yi is 1 plus 0.5 xi. The way I would verbally interpret that is that for a unit change in x, y changes 0.5 added to a baseline of 1. That would be the way I would verbalize the structure of that model. In logistic regression, I would fit a model that looks like this. So my prediction of yi is e to the power of 1 plus 0.5 xi. And verbally, we would interpret that as for a unit change in x, the log odds of y equals 1 changes by 0.5 multiplied by a baseline odds of e to the power 1. That would be the way that we would interpret it. And notice, because now it's a exponential, you have this kind of nonlinearity in how y changes as you change x. It's not just stepwise increases, it actually follows these exponential properties. This makes it a little bit tricky to try to map the regression coefficients you fit in a model to some interpretive value. So we just discussed interpreting from the regression coefficients. That's an inference question. What about a prediction question? Well, in the context of prediction, logistic regression is somewhat tricky because f of x is still a continuous function. Your model prediction of y based off of x is actually a continuous function. And again, it can have this shallow, slow transition. So there could be values of x in which the prediction isn't 0 or 1, it sits somewhere in between. So in order to make a prediction of the state of y, you need to set an a priori threshold where you force y to be one of two values. So in this case, on the example I'm showing on the left, if you set a threshold where the prediction is 0.5 or greater, then you'll decide that indicates that y is in the state of 1. If it's less than 0.5, you decide that y is in the state of 0. So you have to force this decision of pushing y into one of two states depending on that threshold. Typically, the threshold is 0.05 for prediction purposes, but technically that line can be wherever you want it to be. And the position of this threshold determines the bias in your predictions. So if you have a lower threshold, you're going to be biased more towards y being in a state of 1. If you have a higher threshold, vice versa. You could still build meaningful predictions about the state of y from a logistic regression model. You just have to be careful about how you think about this threshold state. And many tools that you might work with in either R or Python by default just set the threshold at 0.5. When does it cross the 50% probability threshold of being 1? So it's just a majority vote, if you will, decision. So just like linear regression, logistic regression will allow for you to make inferences from your data on the relationship between x and y, will allow for you to make predictions of future y given models that you fit. But what happens when y has more than one state? What if you're working with a data type where y has multiple states and they're discrete states? I mean, matter has states that are more than two. It can be solid, liquid, or gas. How do you get a meaningful understanding about the relationship between x and y in that kind of a case? Well, for those types of cases, you'd want to move to a more specialized type of analysis known as discriminant analysis. We're going to go over two types here: linear discriminant analysis and quadratic discriminant analysis. And they're really just two variants of the same thing. In discriminant analysis, what you do is you assume that your data is generated from a set of underlying distributions. You don't really see or touch or really understand completely these distributions. They're intangible, but they exist, and they're the distributions that generated your data. And you assume one distribution for every state of y, for every group that you have in y. And the idea is that the series of x observations you get are sampled from one of these distributions. The question is if I get an observation, xi, which distribution is it generated from? Which distribution does this particular observation come from? So what you have to learn are discrimination boundaries between distributions. So as x increases, it at some point transitions from probably coming from distribution A in orange to distribution B in blue. As it further increases, it probably comes from distribution C in red. And the trick is to infer the underlying distributions that could have generated the data. And for every observation, pick the distribution that most likely produced any given observation. Now, discriminant analysis relies on Bayes' theorem to make its inferences. And just for reference, Bayes' theorem is conditional probability. So you assume that your posterior probability of A given B is determined by the likelihood distribution, which is the probability of B given A, times your prior distribution, the probability of A alone, over the marginal distribution, probability of B. The marginal distribution you can often just assume is 1. And so the prior and the likelihood work together to determine the posterior. So if we plot these out here and I have a particular likelihood distribution and a particular prior, your posterior sits somewhere in the middle. And the position of that posterior distribution depends on the relative mean and variances of your prior and your likelihood. So what you're going to do is you're going to use Bayes' theorem in order to infer the posterior probability of any observation given the prior assumption that it comes from one of a set of distributions of groups. So you're trying to use your group data to infer the shape of that prior that generated the observations that you have. And your goal is to try to calculate these Bayes discrimination boundaries. Essentially use probability theory to infer the separation of the underlying generative distributions. Remember, these are intangible. You can't actually see these distributions. You have to estimate them. But if you make a few assumptions about the nature of these distributions, you can use probability theory to come up with an estimate of any observation originating from distribution A, B, or C. And the way we do it is we actually invert the problem. What we're estimating is the probability that Y is a particular distribution given a single observation xi. So what we're going to do is take the probability of the likelihood of your data, so the likelihood of seeing xi given that y equals k, times the prior probability of that y, which you use based off of labeled data, times the probability of x itself, which we often just assume is 1. So we just say it's the combination of the likelihood of your data and the prior given that distribution. That's how linear discrimination analysis works. Let's say that I have two variables, x1 and x2, and I know that y has 3 levels, a, b, c. A is in red, b is in orange, and c is in blue. LDA tries to infer whether or not you're looking at a particular distribution, your y, given a particular set of x's, as a probability estimate of that distribution k, which we model as pi k, which in this case pi is the prior probability for distribution, in this case k, times some distributional function of your data itself, so f of k xi, over the sum of all the priors and all the other likelihood functions of your data for the other distributions itself. So you're doing it as a ratio of comparing the probability that you're looking at y being in state A, B, or C, given a set of observations x, by comparing every observation to a single distribution relative to its distance to all the other distributions itself. Now, this is linear because we're going to assume a Gaussian form. So if we assume that our data is generated by Gaussian distributions, by normal distributions, then that likelihood function, f of k xi, comes out to being a normal distribution. So we can expand out that fk, just insert the definition of a Gaussian distribution with a mean mu k. And in this case, we're going to assume the variance is sigma squared, a capital S sigma. As long as we assume a particular mean and a particular variance for each distribution, which again, if you have labeled data, you can calculate both, then for any observation that we have, we can predict the likelihood that it belongs to distribution k, i.e. distribution A, B, or C, by comparing its likelihood for distribution k to all the other distributions. Essentially what you're asking is an individual observation closer to distribution A than it is to distribution B and C? If so, we'll say it comes from distribution A. This is all about distances from centers of distributions, distances from those means. Now, in an ideal world with Gaussian distributions, the optimal separation of distributions falls at this kind of intersection point of the two curves. So let's say that I'm looking along a one-dimensional line. So your x-axis here on these two distributions goes from negative x to positive x. So as I keep increasing x, it's very likely at the beginning that it's pulled from distribution I, the orange distribution, which has a mean of mu I. As long as the probability for mu I is higher than the probability for mu k, or in other words, as long as the ratio of the probabilities that an observation belongs to distribution I as opposed to distribution k, you by default assume that it belongs to distribution I. As soon as that ratio flips, which is at the point here shown by this dashed line, you've crossed the Bayes decision boundary, the optimal decision boundary that separates the two distributions. And you can assume, because the likelihood is higher for a data point to be generated from the other distribution, you can assume it belongs to that distribution. So the Bayes decision boundary you can just boil down to being that position between the two means, so long as the variances are equal. If the variances are equal, the equal distance between the two means is the position of the Bayes decision boundary. And really all you're doing with this decision boundary is saying observations on one side belong to one group, observations on the other belong to the other. If you think about the two distributions shown here on the left as being likelihood distributions, then everywhere that it's orange, a new observation is likely to come from the orange distribution I. Everywhere that's blue, you assume the likelihood of observing that data from the blue distribution. If you take the ratio of them at every point, as soon as the likelihood for I in orange drops below the likelihood for K in blue, that's the point at which you transition your decision from saying I to saying K. It probably helps to see this in a two-dimensional setting. Let's go back to our three groups here. We have our states of Y, A, B, and C. Now, we can calculate out means for all three groups. This is labeled data. We know what each observation's Y is and what their X1 and X2s are. But what happens if we get a new data point? Let's say that we have a new Xi here. The question is which group does this belong to? Well, normally what you do is you say, okay, how close is it to this mean here? Let's just look where this crosshair is the mean for group B. And we compare it to the means for group C, shown in blue here in the crosshair, and group A. And we're asking, how close is it? What's the likelihood it was generated from a distribution centered here in B compared to the other two distributions? So what you actually calculate out is for that value xi, a discriminant function. And you calculate a separate discriminant function for every group of y. And the discriminant function is just a variant of that Bayes decision boundary, where you compare xi relative to the mean for group K, let's say B in this case, and you're just normalizing that difference between the two distributions by a log of pi k, which in this case, pi k is just the number of observations in that one group over the total number of observations you have in your data set. So in this case, it would be the number of orange dots relative to all the dots on my plot. So it's a slightly normalized version of that Bayes discrimination boundary. And really what that's telling me is how close is this dot to this mean compared to this mean and this mean. As this discrimination function increases for a particular distribution and a particular observation, it means that observation is most likely to arise from that distribution. This is how LDA works. It tries to calculate this discriminant function for every observation and then assign it to the group that it's closest to. The assumptions for LDA are that any observation is multivariate normal random variable, all the generative distributions of the same variance, sigma. There is no collinearity between groups, and all of your errors are independent. Basically, the equal variances assumption here just specifies that in the context of like two or more dimensions, the discrimination boundary is a straight line. But there are often cases where that assumption of equal variances isn't met. Consider a case here where I have two distributions that define two different states of y, but it's clear that the variance for one group is much bigger than the variance for the other group. LDA wouldn't work here. However, a variant of it, quadratic discriminant analysis, will. The difference between quadratic discriminant analysis, QDA, and linear discriminant analysis, LDA, is that QDA removes the assumption of equal variances and the decision boundaries become curves instead of straight lines. That's it. All the other logic of the approach of LDA applies to QDA. It's just a modification of that discriminant function. So here, we're actually having to identify and fit the variance for each distribution as well as the mean. You're no longer just going to assume that all of them have the same variance. You're actually going to have to calculate and estimate the variance for each underlying generative distribution separately. That's the only additional step. But that gives quadratic discriminant analysis much more flexibility at doing classification. So the assumptions of QDA are just simpler than the assumptions of LDA. You still assume that xi is a multivariate normal random variable. You assume there's no collinearity between groups, and that the errors are independent. All you've removed is that equal variances assumption. So this makes LDA and QDA very powerful tools. And QDA, it being more flexible, means that it's going to be on the more variance side of the bias-variance trade-off compared to LDA. But you can imagine many cases where this assumption about equal variances doesn't hold. Now, importantly, LDA and QDA can work with just two groups as well. So they can do the same process of classification as logistic regression. However, their application is mostly in the prediction case. You're not really building an intuition about the relationship between X and Y here. These are primarily prediction models. You're learning to predict states of Y from X. And they're very powerful as prediction models. But inference about the distributions themselves gets tricky. You can recover the underlying means and variances and try to make an intuitive understanding about the relationship that way, but it doesn't have the same elegant mapping as what you have with logistic regression. So you can think about discriminant analysis as being more on the prediction side, and logistic regression being more on the inference side. But I hope you can see that while logistic regression offers an intuitive extension to linear regression for classification problems, discriminant analyses like LDA and QDA are more flexible for classification in cases where your data consists of more than two categories, something that we see a lot.